In this video, we will discuss universal gravitation, a concept that was worked on by Sir Isaac Newton and culminated with the development of this formula which I have written below, where the force of gravity is equal to a gravitational constant, which he called G, times mass 1 times mass 2 divided by r, which is the distance between the center of those masses. G he found to be 6.67 times 10 to the negative 11, and the units of G were found to be the Newton times meter squared divided by kilogram squared. But what exactly is this force of gravity? Well, he found that all objects that have mass attract each other with a gravitational force. Now, what better mass than to talk about Earth? So when we look at the Earth, we could see that the Earth is attracting all smaller objects in the vicinity towards its center. That's what all the arrows pointing towards Earth's center represent. That's the gravitational field that Earth is creating because of how large its mass is. And because of it, like I said, all objects will be attracted towards its center, including us. If there was no surface of the Earth, we would continue to fall until we hit Earth's center. But because the surface is there, we are able to walk about each and every day of our lives and not be pulled towards its center. Now, we were found in the first couple of chapters that the acceleration due to this gravity was 9.8 meters per second squared. Now, later on, I will show you exactly where we get that number from, and it is derived from this formula of gravitation. So let's get right into this formula. Let's see what let's talk about this formula and see exactly what happens when we manipulate certain parameters of this formula. Well, what happens when we increase the distance or increase that radius between the two objects? Well, let's see. So we're going to say we're going to increase the radius. So increase the radius. What does that do to our force of gravity? What happens? Well, this is very similar to all the other formulas that we were talking about throughout the year. Since r is located in the denominator of the right-hand side of the equation, we can see that it must be inversely proportional to Fg. So anything we do to r has to be flipped, per se, when we're talking about the force. So if we increase r, we can see that we would then decrease the force. By how much? Well, let's analyze that. Okay? So if we, let's say, double r, what happens? Like, I see I made a little bit of a mistake. I just want to go back and just add a 2 because it's the r squared. It's the distance squared. So if we double r, what happens to Fg? Well, let's look at that. If we put 2 in for r, and we'll rewrite the formula right to the right. So we have Fg equals G, that gravitational constant, times m1, m2 over now 2r squared. What happens? Well, we see that that square does something. So that 2r squared can be written as 2 squared, so let's write that as 2 squared times r squared. Now, since we can write it like that, we see right away that the 2 squared becomes a 4. So it's really saying 4 times r squared. Now, since the r is located in the denominator, we see that to the whole right-hand side, we added a 1/4. Now, let's see if you can't see it, I'm actually gonna write it. If we have Fg, and we said that that's equal to G m1, m2, and we said 2rn squared, we can say that this is r squared, and we just said that there's a 2 there. So this 2, I'll draw an arrow where it comes here, like so, becomes, in a different color, 4. So we have 4r squared. Okay, but really, we can think of this as 1 over 4. Alright? So since we multiplied a 1/4 to the right-hand side of the equation, we must, to keep it equal, multiply a 1/4 to the left-hand side of the equation, like so. Now that shows when we double the radius, or double the distance between our two masses, we must quarter the force. So the force quarters. So every time the distance gets larger between those two masses, the force goes down by a factor of 1/4. Like we said before, we increase the radius, the force must decrease. Let's try another one. If we quarter the radius, what happens now to the force of gravitation? So we quarter the radius. The objects have gotten closer. So since the objects have gotten closer, the force of gravity must increase. Increase by a factor of what? Let's write this out. Okay, we'll write it over here. Again, force G equals the gravitational constant, m1, m2, over now 1/4 r. And remember, it's squared. It's saying 1/4 squared times r squared. And what does that equal? We can see that that equals 1/16. So this is really 1/16 times r squared. Okay, since 1/16 is now in the denominator, we must do what? We can see that 16 must be added to the other side. Again, if you don't see it, I'll write it out nicely using a different color. Okay, right here I'll write it out. We have the G times the M1, the M2, all over now 1/16. Let me rewrite that. 1/16 r squared. Staying true to algebra, we rewrite this. G over M1, M2 over r, and because we had that refraction in the denominator, it now becomes in the numerator. And there's multiplications between them. Okay, I'll rewrite so you say it. There's the equals, and it's like saying 16 over 1 times that. Okay, since there's 16 now in the right hand side of the equation, there must be 16 on the left hand side of the equation. So going back to what we said over here, if we quarter the radius, if the radius is brought in by a factor of 1/4, what happens to the force? The force increases by a factor of 16. Again, we said that this is the inverse square law. Okay. Alright, so now that we talked about the distance, you know exactly what happens when we increase the distance or decrease the distance. What happens when one of the masses gets larger or gets smaller? Well, we can see that the m's are located in the numerator. So because they're located in the numerator, you know that they are directly proportional to the force. So whatever you do to the mass, you must do to the force. So let's think of this as, let's try this problem. If we quadruple mass 1, what happens to the force, or the gravitational force? One of the masses increases in size by a factor of 4. Well, the force will increase by a factor of 4. Well, what happens if one of the masses shrinks? One of the masses shrinks by a factor of 1/2. So mass 1 now is 1/2 smaller in mass, 1/2 smaller. What happens to the gravitational force? Well, it's directly proportional. So the gravitational force has to be also halved. Okay? Hopefully you can see that. Those are some of the types of questions that the Regents will ask. It's just analyzing the formula and knowing how the formula works. Remember, the mass is directly proportional to the force of gravity, the gravitational force, and the r, the distance between the two masses, is inversely proportional. And we said it's the inverse square law. That anything that you do to the radius or the distance, you must square it and flip it. It's the inverse. You flip it, and that's what you will have to do to the. That's what would happen to the gravitational force. All right. So for the first question, we see what is the gravitational force of attraction between two asteroids, each with a mass of 50,000 kilograms, separated by a distance of 3,800 meters. All right. Well, the first thing we want to do is we want to gravitational force of attraction. So underline that in red. Gravitational force of attraction. As soon as you see that, you know you're going to use the equation Fg equals G times m1 m2 over r squared. Okay? Next, let's draw exactly what we are talking about. So we have two asteroids. So we'll draw this in red. We have two asteroids. Here's asteroid number 1. And here's asteroid number 2. And I'm going to put a dot in their centers, because the reason being the distance between them is measured from their centers. Okay, so here's that center and here's that center. The center of their masses. And we found that to be 3,800 meters. Now, each of them are going to have a force, so we're going to have a force vector going this way and a force vector going that way, and we're trying to see what that force G is. What's that gravitational force? Alright, so it's basically just putting in the information into our equation and solving for Fg. Now, from our reference table, we are given what the G constant is. And we said that the G constant is 6.67 times 10 to the negative 11. And we said the units for that were the Newton times the meter squared over the kilogram squared. Now that, let me move over our drawing a little bit so we could fit everything in. I'll just move it over. Just give me a second. I'll just drag it over there. Okay, and we can see that then the G is multiplied by 50,000 kilograms, and then another 50,000 kilograms. Those two 50,000s represent mass 1 and mass 2, the two masses of the asteroid. That whole thing is divided now by the distance. The radius between them is 3,800 meters, and that is squared. When we do the math, we find that Fg is equal to 1.15 times 10 to the negative 8. And what are the units? It's the Newton. Alright, for the next question, we have, suppose a 100 kilogram astronaut feels a gravitational force of 700 newtons when placed in a gravitational field of a planet. We want to find A, what is the gravitational field strength at the location of the astronaut, and B, what is the mass of the planet if the astronaut is 2 times 10 to the 6th meters from its center. Alright, so let's try to first draw a picture of exactly what's happening. Well, if we have some planet, I'll draw it like this, and I'll label this as P. This is our planet. And we have some astronaut out here, and he is being pulled in to the planet. I'll draw all the force vectors so you realize that there is a gravitational field from this planet, because this planet is nice and large. It's a big mass, so it's creating a gravitational field and pulling all objects in the vicinity towards its center, which we discussed before. Alright, so we want to find what is the gravitational field strength. So what exactly is the gravitational field strength? Gravitational field strength. It's the acceleration due to that force. So let's rewrite this as the acceleration due to the gravitational force. Alright, so if it's the acceleration due to the gravitational force, what equation could we use? If we know a force, if the gravitational force is 700 newtons, and we know the mass of the object, which in this case is the astronaut, which is 100 kilograms, what is that acceleration? We can use the equation of F equals ma, where the force is 700 newtons, and that is equal to the mass of 100 kilograms times the a, or in this case the g. So when we divide by 100, we can see that the a, or you can say the g, equals 7 meters per second squared. I'll box that in. Alright, and for question number B, what is the mass of the planet if the astronaut is 2 times 10 to the 6th meters from its center? When we see mass of a planet, and we're talking about two masses, you know you're going to use the universal gravitational formula, where it's Fg equals G m1 times m2 over r squared, which is the distance between them. When we plug in the information we have, we see that the force of gravity, the gravitational force, is 700 newtons. We were supplied that from our problem. And that equals the gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. And that will be multiplied by 100 kilograms, which is the astronaut, times mass 2. And that's all divided by the radius, which from the problem says it's 2 times 10 to the 6th meter, and we remember the distance has to be squared. So when we do our basic algebra, we see it's 700. I won't write the units, just try to remember the units, times 2 times 10 to the 6th equals the gravitational constant, which is 6.67 times 10 to the negative 11 times 100 m2. And we find that m2 comes out to be 4.2 times 10 to the 23rd kilogram. I'll box in this answer. And now for the last question. If the space shuttle orbits the Earth at an altitude of 380 kilometers, what is the gravitational field strength due to the Earth? Again, let's underline what we're looking for. So we're looking for the gravitational field strength. That would be small g. Alright, so first thing, let's draw a picture. Let's see exactly what's going on here. So if I have the Earth, say that's the Earth, I'll draw the continents really quick. Okay, there's the Earth. And then we can draw the space shuttle. There's the space shuttle. And we could say that the distance between the space shuttle and Earth, they said, was 380 kilometers. So we could put 380 kilometers. Alright, so that's what we're looking for. And now we're looking for the G. What is that gravitational field strength? So we know the gravitational field strength on the surface of Earth. So we could say G surface is equal to 9.8 meters per second squared. Now, not only on the surface, but very close to the surface. Could still be a little bit of a fluctuation of 9.8 meters per second. So what is that G value when we're 380 kilometers above the surface? Well, let's find out. Using the equation that we've been using for a month now, F equals ma, we know that G would equal a, the acceleration due to gravity. So we could rewrite this as m times g. And now g we know is the gravitational field strength. But now what else does Fg equal? Well, we know that the force, this force right here, is Fg. And that's also equal to big G times m1 times m2 over the distance squared. So since Fg is equal to G m1 m2 over r squared and also ma or mg, we can rewrite these two equations. We're going to put them together and we get mg is equal to the gravitational constant times m1 times m2 over r squared, the distance between them. So that's the equation we're going to use. Now when we look at this equation, we see that m1 and m2 on the right hand side, and we have this m on the left hand side. What is that m on the left hand side? Well, the two m's are for the two masses that we're trying to find the attraction for. So we could really say m1 times g is equal to the gravitational constant times the two masses over their distance squared. So when we see that, we can do some algebra. We could now divide the right hand side by m1. And whatever we do to the right hand side, we do on the left hand side. So we divide this entire thing by m1. And we're left with g equals big G m2 over the distance squared. That's great. So now we have our equation. We have the g on the left-hand side, which we're solving for, which is the gravitational field strength, and we have all the information on the right-hand side that we can fill in. So let's do that. So we say that g is equal to the gravitational constant, which is 6.67 times 10 to the negative 11 times, what's the mass 2? Well, the mass 2 would be the mass of the Earth. So the mass of the Earth we can find from our reference table as 5.98 times 10 to the 24th kilogram. And that whole thing is divided by the distance between the space shuttle and the distance between Earth's surface. Now here's the important part. Earth's core, the center of Earth. So we know that from the surface it's 380 kilometers. Okay? What is that in meters? Well, 380 kilometers would be 380,000 meters. But that has to be added to now the radius of the Earth. So what's the radius of the Earth? So what's the center of the Earth, which I'll draw right here, to the surface? So we're looking for I'll put that in a different color so you can see it. What is the distance between the center of Earth and its surface? Again, we can find that in the reference table. I'll write that in a different color down here also. But from the reference table, it says that the radius of the Earth is 637,000 meters. So that's the distance. The distance is the radius of the Earth plus the altitude of the spaceship. We add them together, and then we'd have to take the square because that's the distance squared. When we do all of our computations, we get that g is equal to 8.75 newtons over kilograms. And we know that that would then be called 8.75 meters per second squared. So I could box in that answer. I just want to fix this typo before we move on. The radius of the Earth is 6,370,000. So I just want to make sure we know that. It's on our reference table. But the right answer is 6,370,000 meters is the radius. So the distance between the space shuttle and the center of the Earth would be the altitude, which is 380,000 meters, plus the radius of Earth, which is 6,370,000 meters. You add those together, that's the distance between the two objects' center. Then you would do the computation, and you would find that the gravitational field strength is 8.75, which we could see is lower, about 11% lower than it would be on Earth's surface.